Okay, let's start. This is the topic from where we have to start. Previously, we were here translating from English to logical expression. And
Do I have to upload it to the record?
no, just physical summation. And now this one using quantifiers in system specification. This has the same idea as you saw here. Previously, we saw this only part one, this part two was remaining as I am thinking. I don't know, maybe the case was with this class or that class. So, what was the last slide according to your understanding? So, this is something, it is written here, read it yourself, so nothing else. We will see this premises and arguments and conclusion in the next chapter also. Just to save the time, it is written here, read it yourself. Otherwise, it is not something difficult. These statements are converted into this px, qx, and rx, etc., etc. Nothing else. This is not a big issue. Now, this is the topic from where I have to start, and this is nested quantifiers. Previously, we saw quantifiers with respect to their exist and also for every. Now we are going to see the nested quantifiers, and in this, we are going to translate or convert logical expression into English. So, here in this example, a logical expression is like this: for every x, for every y, x greater than 0, which means the positive number, and y less than 0 implies xy less than 0. So this statement is given. Translate into English. This is asked. So this mathematical expression or logical expression is given, and you have to translate it in English sentence. Where the domain for both variables, what are both variables? X and Y. Where the domain for both variables consists of real numbers, and real numbers include negatives and positives and fractionals with decimal points and the whole numbers. So you have to convert. What is this saying? For every x and for every y. And if you have to just focus on it, x greater than 0, which means x is a positive, which means x is a positive. And this y less than 0, which means y is negative real number. X is positive real number, y is negative real number. So what it is saying that any value from the domain real value, any value for x and any value for y. If x is positive and y is negative, then this implication means then, according to your previous knowledge, and then the product of x and y, multiplication of n x and y, less than 0 will be negative. So now you have the sentence in your mind. Now you have the sentence in your mind. So this is just theoretically written here, nothing else. So the statement says that for every real number x and for every number y, if x is positive and y is negative, then xy less than 0. So it is just explaining that this statement is saying this, and that. Separately, he is just discussing things separately, nothing else. That is, this statement says that for real numbers x and y, if x is positive and y is negative, then xy is negative. More clearly, the product of a positive real number and a negative real number is always negative. So this is the sentence. This is the answer. You don't have to discuss this whole stuff. Not needed. You can only write this last sentence as an answer. Tamam. But this is for your understanding. This is for your understanding that how we reach at this statement, last statement, how we reach at this statement. Otherwise, you can see here we are using x and y. So this is positive, this is negative. So more examples will come and you will see. Now this is the table, and these are some laws or rules that you have to memorize for the quantifiers. And here, so these are the rules. Here for every x, for every y, whatever the value of x, whatever the value of y. And this is the statement. For every x, for every y, this statement, when it is true, it means that for every pair of x, y, or you can say for every x and for every y, p of x will be true. And when it will false, put the negation here and move the negation forward until you reach at this point. And what will happen? There exists x, there exists y, it will be converted. And then negation will be here before the p. And then, okay, if there is, then you can just describe that mathematical conversion into a sentence. For example, there exists x, there exists y, and then negation pure p x y. Now say it in English sentence. So there is a pair xy. There exists. So there exists a pair xy for which this p of xy is true, but this due to this negation it becomes false. So there is a pair xy for which p of x is false. So this is the situation when this and that, this is the same thing. Only y is written first, x is written after. And then when it will become true and when it will become false, this is the situation written here. For true, you have to read it like that. Both? No. They have the, if you have the domain real numbers, then x can have some value from the real numbers, y can have the value from real numbers. So this is what, these are only rules. So x and y may have different values, may have same values, because these variables are taking values from the domain. So these are the different laws that you have to keep it in your mind. Now this one, what is saying? For every x, there exists y, p of xy. So this is statement. So if you don't have any negation, it means p of xy is true. For what? For this case. For this case. When this statement will be true? For every x, there exists y for which this statement is true. So this is, you have to say when it is true. For every, what I am saying, I am just translating these mathematical notation into English sentences, nothing else. For every x, there exists y for which this statement p into xy is true. And when it falls, put a negation and move the negation forward until you reach here. So now I have the negation here and these will be converted. There exists x for every y. So now you can say there exists, or there is an x, or there exists an x for which p of x is false for every y. Or you can say there is an x for every y. Okay, there is an x for every y for which p of x is false. It is up to you because it is a sentence. And same is the case here and here. For saving time, I am stopping. You can just read. It is quite easy. And just remember, you have to memorize these things. So now we have an example. Express the statement. Express the statement. Everyone has exactly one best friend. So this is a statement. Everyone So from everyone, you can understand that maybe now for every universal quantifier will be used here. Everyone has exactly one best friend as a logical expression. So express this sentence or convert this sentence as a logical expression, which would be mathematical, you involving or using predicate and quantifiers. Predicates and quantifiers. Quantifiers, you know that, and predicates, we saw these things in the previous topics. With the domain consists, and the domain consists of all people in the world. And logical connectives, and or disjunction, conjunction, these are called logical connectives. So convert this sentence into a mathematical form, into a logical proposition or logical expression. So these are the different words. You can use general word expression. So now, okay, the theoretical things are written there. We have seen theoretical things again and again. So now I am just moving directly here. Everyone has exactly one best friend. Look at this mathematical notation. Does this logical expression, does this answer is giving you that understanding of the sentence? So for every x, everyone has exactly, what is the domain? All people. So everyone has exactly one, exactly, the word is exactly. There can be word, there is a friend, but the word is exactly. So now you are going to see another quantifier, which is called unique quantifier, okay? This is called there exist and this exclamation symbol together. So this is called unique quantifier. What is the name for this quantifier? Unique quantifier. So for every x, for every people, you can say, for everyone, there exist exactly or unique y. There exists a unique y, and b of x is what? It is called predicate. Y is a friend of x, you can say. Maybe it is written here. B of x, y to be the statement, y is the best friend of x, okay? It is written there. You can explain these things first, and then you can give the logical expression. So b of x, what is the meaning of the b of x that you are taking from this sentence? We are taking b of x, y as a predicate, and we are saying it is equal to y is a friend of x. And y is what? There exactly. This condition is with y, and this condition is for every x. So for every x, there exists exactly one y, and that y is a friend of x. So that is now, is it all the meanings here are covered in this mathematical answer? So all. So that thing is theoretically discussed here, just to save my time, because stuff is quite lengthy. And we have seen these things already again and again. So this is the logical expression. And for every, this is giving for the meaning for every x. And there exists I is giving exactly one. This concept exactly one is here. There exists an exclamation symbol. There exists y. And b of x is for what? Y is the best friend of x. Okay. Next. Express the negation of the statement. So this is the statement given to you, and it is asked, express the negation. So put the negation symbol here and move it forward. So express the negation of the statement. So what it is saying, what is the negation of this logical expression? So that no negation precedes a quantifier. And you have to do the negation in such a way that the negation cannot be placed here in the front. It will be here at that. So no negation precedes a quantifier. No any negation before these quantifiers. So we will put the negation in the first position and then we will move it forward up to this position, and then it will happen what? Negation is now not with the quantifier. So how you can do that? Put the negation before it, and this would be the situation. Negation for every x, there exists y, x, y is equal to 1. This would be your first step. Put the negation in the beginning. And then what? What you can do with the negation? You can move the negation forward. And if you will move the negation forward, the quantifier will be swapped, you can say, or it will be converted into the opposite quantifier. If yes. You can just provide the final step, or it is better to start with the first. It will only 2 or 3 steps, nothing else. So this would be the first step. I am not reading now theories, okay, just to save my time. When some new thing will come, then I will pass more time at that topic. So negation for every x, there exists y. So this was the logical expression given to us. We only have put or placed negation at the front. And now what is the next step? We have to move this negation forward. When this negation will come here, before the there exists, then this will be converted into, this for every will be converted into there exists x. Like that. It will be, this will be converted into this one, there exists x, and negation would be here now. And now move this negation further forward. Move this negation further forward, and this will be converted into the universal. Existential will be into universal. And this is now the situation, and your negation is this here. What it is saying, product of xy is equal to 1. Yeah, this was the previously said. And now it is negation. How you can put it? You can just, what you can do next? How you can represent this with some other statement? Xy not equal to 1. Here it was xy is equal to 1. When it will become false? Here you have the negation. What is the meaning of negation? That xy is equal to 1 is now becoming false. And what is the false for this one? Xy not equal to 1. The false condition. So that's why we are representing finally it with there exists x for every y. This is the same thing. There exists x for every y, and xy not equal to 1. And now that negation is gone. So this is our final form of this logical expression. This is not a difficult thing. Now, this topic was not in this chapter, but now I have inserted this topic because this is important. By the way, from the definition or from the statements of CEOs, I can skip this topic. But this is important. So that's why I put it again in the slide. So rules of inference. Actually, all the things that you study before means from the beginning of this course, what are the different things that you are studying? Actually, all those things are for this topic. Actually. So anyhow, rules of inference. First, you will see some definition here. And it is, we will see some arguments in this topic. We will see some arguments in this topic. Arguments is a term now. Now, this word argument is a term in this topic. So an argument form in propositional logic. So whatever propositional logic, whatever the rule that you have studied in mathematical type thing, P implies Q or conjunction or dissonance, whatever you have seen. Something will be presented into the form of an argument form, into the form of a propositional logic. So now we are going to see what is that actually. So an argument form in propositional logic is a sequence of compound propositions. Sequence of compound propositions. You will have one proposition, then another, then another, then another. A sequence of compound propositions. And those propositions will not include sentences. It can include sentences, but it will include propositional variables, A, B, C, X, Y, Z, whatever. So now you will have the compound propositions in sequence, one after another. And the whole thing, that whole sequence is called argument form, are called simply argument. That argument can be valid or invalid. And an argument will be valid when the conclusion is true. When you will have different compound proposition, for example, this is the first one, first proposition, then second, third, fourth, fifth, and then there would be the last statement. That last statement normally called conclusion. In this structure, in this argument structure, you have first the sequence of propositions in mathematical form or in sentence form, and at the end you have the last statement that is called conclusion. So now we are going to say which argument is valid and which argument is not valid. So an argument, I am just removing this word. An argument is valid when the conclusion is true. And there is a condition, if the premises are all true. All those propositions that is before this last statement, which is conclusion, all those statements which are written before this conclusion, these all statements are called premises. What are these called? Premises. The other name for these propositions, compound propositions, which are written in sequence, the other name for these is called premises. And this last statement is called conclusion. So an argument will be a valid argument if this conclusion is true. If conclusion is true and if all premises are also true. All premises, all propositions in sequence, they are true, and then conclusion is true. This is a valid argument. If conclusion is not true, then it is not a valid argument. Or if anything wrong in the definition of a valid argument, that is invalid. So now it is mathematically written here that if you have the premises like P1, P2, and so on, Pn, and the conclusion is Q, then P1 and P2 and Pn, these premises will be true. Only then Q is true. If this is the situation, then this is called tautology. So anyhow, keep this definition in your mind. Now, rules of inference for propositional logic. Now we are moving on to, this is the table which has all the rules for this topic. We are now, from this slide, we are now moving slowly to that table. So by using, now you know that an argument can be valid or invalid. When you normally prove an argument is a valid argument, then you normally use some rules. Those rules are called rules of inference. Okay? When you normally prove an argument when you normally prove the validity of an argument through some rules, those rules are called rules of inference. For example, here we have the tautology. Basically, this is a logical proposition, but we are saying it tautology because it will have the final columns true. So that's why we are calling it tautology. Otherwise, it's not a difficult thing. I know that maybe some students are not getting my point. The reason is that they were not alive at some point previously, and now they are not understanding. Okay. Only reason is this one. Previously, they were not alive at some point, and now that empty space is creating an issue in their mind that they are not understanding those things. But believe me, what I can do, I have only 35 minutes. In 35 minutes, what I can do? I am sad from my inside because I want to convert the true concept. But what can I do? I want to finish this CO, inshallah, today. Let's see. So this is a tautology. This is a logical proposition which is called tautology. And it is P and then parenthesis, P implies Q and then implies Q. Which is basically, this P is here and then P implies Q. This P implies Q is here. And when you have the things like that, according to our previous definition, these premises normally have the and between them, either written when you have the things like that. These are the sequences of compound proposition, P1, P2, P3. So and is automatically implicitly there. By default, and is there. You don't have to mention, it is there. So P and this. And here it is called therefore. This symbol is called therefore. You already know that from mathematics. Therefore, Q. So this thing which you are seeing here is written in some mathematical form or is written into the form of an argument here. These above the blue line, these things are premises and this is conclusion. And this law which we are seeing here is called the modus ponens law or law of detachment. Modus ponens is a Latin word, also means mode that affirms, something that confirms something. Okay. Premises, if it will be true, that will confirm that the conclusion is true. So anyhow,
The prior to the P implies Q. It's in the parenthesis. Why it's not the case? P here.
It's not an issue. You can write it and at any position because these are only two. You can write this one first, this one after, or this one. So this is not an issue because they are only two. It will not create any disturbance. So this is called conditional statement or implication. And this is called hypothesis in a modus ponens rule. This is, from this arrow, you can say it is conditional statement. What is the name for this arrow? Conditional statement, implication, single arrow, whatever you want to say. There is a double implication, biconditional. I don't want to say those things again. You can just refer back to those slides and then you will understand. So this is an example of implication. This is hypothesis. And in the modus ponens, these are true. So this law is already proved. You only have to keep it in your mind. You will see this in the table. So if these are true, then the conclusion is also true. So this is a law now, which is called modus ponens. And P implies Q. This is okay. You can, for just to memorize, This P is same, the remaining is Q that is there. This is a trick to just memorize, nothing else. Now we have an example. Suppose that the conditional statement, now this is a sentence is given to you. Conditional, which will have conditional state. Conditional statement is what? Arrow. If it snows today, this is if, this is then. From this written pattern, you know that it is implies something. So if it snows today, then we will go skiing. Skiing on the snow. And its hypothesis is it is snowing today. So this is one sentence, which is in the form of P implies Q, like that. Like that. If I will say it is P and if it is Q, then how can I use P implies Q? And its hypothesis is it is snowing today. So this P. So this is P implies Q, this is P. Again, now they both are true. Then by modus ponens, what would be the result? What would be the result? What would be the resultant sentence? This one, we will go skiing. Yeah. We will go skiing, which is written here. It follows that the conclusion of this conditional statement, we will go skiing, is true by using modus ponens. Now there is another thing mentioned here, that a valid argument, if you have a valid argument, can lead to a incorrect conclusion. It can happen that your whole argument is not valid when one of your premises is false. According to the definition, if you have P1, P2, and so on, Pn, if any P is false from the premises, then your conclusion is false. This is another example. It's easy, not different, not difficult. I can start and then I will leave and I will go to the next. This is an example showing that determine whether the argument given here, whatever the arguments given here, is valid or not. Determine, identify this, solve it, and determine whether its conclusion must be true because of the validity of the argument, and also determine that if the argument premises are true, then the conclusion is also true or not. So here, if this is P, then this is Q. Okay? We know that 2 under root, this one, 2 under root greater than 3/2. Consequently, you can calculate. Or if you will take the square, you will have 2 here and 3/2 here. If you will divide whatever, it would be 9/4 if you will divide. I don't know it is greater or not, I don't know. You can do it through calculator. A little bit is mentioned here. So what we have to conclude, that this argument is valid or not, nothing else. If the argument is valid, then the conclusion is true, otherwise conclusion is false. And here the argument is false, which means the conclusion is also false. And all the things are mentioned here. When you will read it, you will understand it. Nothing. When, for example, you can calculate 4.5 something. If you will calculate, then everything will be clear to you. Only thing is you have to calculate these things. And then you have to check that this condition is true or false. And everything will be clear. So moving forward forcefully. Now we have a table here. The first rule is the modus ponens rule. P and P implies Q, therefore Q. This is the same rule that you have seen here. Okay. It is called modus ponens. It is called, these are the rules of inferences. It is called modus ponens. You can write it in like this, P and P implies Q, implies Q. How I can write? Can I write it like that? I told you that there is an and already exists between the premises. And here we are using and, nothing else. And therefore, if all these premises are true, then conclusion is true. So then, due to then, this arrow is there. Or you can say due to therefore, this arrow is there. And then Q. And then you have this rule, negation Q, P implies Q, and therefore negation P, it is called modus tolerance. You have many rules. Hypothetical syllogism. I can read and I can say their names, but I am saving time. And I will move here directly. Disjunctive syllogism. Here you have P disjunction Q and then negation P, and it is equal to this one. And this P, therefore only one premise. And then you have P disjunction Q. This is called addition. And this form is equal to this one, okay? All these forms are equal to each other. This form is equal to this one. This form is equal to this one. Same is for all the cases. We have simplification, conjunction, and resolution. And now we will see some examples. And then in those examples, you will see that these, somehow we will use some of the rules which are given here in this table. This is an example which, and it is asking state, describe, and what is the Arabic word? Also. Okay. Which rule of inference is the basis of the following argument? An argument starts from here. And the question is asking that in these sentences, or in this argument, which is written in sentence form, what rule from this table is used? What rule from this table is used here? To identify that rule, we have to understand these sentences. And what it is below freezing now. This is one sentence. It is below freezing now. You can call it P. Therefore, it is either below freezing or raining now. You can also say it either. Okay, it is up to you, different accent. Due to Germany, I normally say either. Okay, my habit is now with respect to Germans. So therefore, it is either below freezing or training now. So therefore, it is either below freezing. This is the same P as you have here. And this is different. Or means disjunction. Raining now, or it is raining now. This is different. So this is Q. If you say that this is P, then below freezing, either below freezing, this is again same, it is P. And if it is Q, then you can say P, therefore, this might be the rule used here. P, therefore P disjunction Q. So the question is asking which rule is used here in these arguments. And now you can understand this one, P, therefore P and Q. You can say it is addition. So from this table, this rule is used. this rule is being used here in these sentences, and the name of this rule is called addition rule. So this was a small question. Just want to check that have you that ability to identify that if there are sentences in front of you, can you identify that according to what kind of rules these sentences are written there? Now we are moving towards some complex examples.
Should I use the name of or not required?
What?
The name of the
Addition rule? Yeah, it is written there.
should I use it?
Why not? Only then I can believe that you memorized all the rules. If you will not, you only know the rule by looking at the sentences, then I can understand that you don't have that understanding. Anyhow, state which rule of inference is used in the argument. An argument is given here. Now again, you have to, at least you have to describe that what type of rule is used here. Now you have to read it. If it rains today, so this is first sentence, then, we will not have a barbecue today. If you say, and, so maybe we will see, first read it and then use some variables. Because it can happen that sometime you have to use P or Q or what for a negative sentence, because there is no positive sentence in the question given to you. If all are negative are like that, all evidences are negatives, and there is no positive sentence, then there is no need to use a positive variable. Use that P for the negative sentence. Anyhow, if it rains today, then we will not have a barbecue today. So these are the two sentences in it, and it is P implies Q. Maybe, I don't know. If we do not have a barbecue today, which is this one same, this is a negative, this is also a negative. And if we do not have a barbecue today, then we will have a barbecue tomorrow. So this is again if then else. And therefore, it rains today. And therefore, it rains today.
Same.
Then we will have a barbecue tomorrow. It is different. It is just a story which is giving you the premises and the conclusion. From the previous sentences, you can conclude that what is the situation in the conclusion. So if P is the proposition, it rains today. If this is P, and if this is we will not, if it is Q, this negative, we will not have a barbecue today. If it is Q, then what it is saying, then we can write this whole sentence into this form, P implies Q. If we do not have a barbecue today, which is what? Q, then we will have a barbecue tomorrow. This is something different, which is R, you can say P, Q, R, S, T, U, you can go on like that. And this is in the form of if then, so you can write it also in this form, Q arrow or, and then therefore, due to therefore, you can put these three symbols. If it rains today, this is the P. Okay, this is the P. This is the P again. We will have a barbecue tomorrow, which is R. Okay, you can write it. After writing it, now compare it in your mind with the table. Compare it with the table. Which rule it is? P, Q, QR, PR. So go on in this table. That is in your mind. P, Q, QR, PR. Maybe this one. P implies Q, QR, PR. So this is called hypothetical syllogism. So now you can answer this question where it is. In this argument, hypothetical syllogism is used. Okay. Now another one. Now using rules of inference to build argument. To build argument. Using rules of inference. This is just a additional information that if in your question or in your problem, you have many premises, then you maybe needed several rules of inferences to show that the argument is valid. You can also prove it through the truth table. All these things that you have seen here, you can also do with the truth table. But when the number of variables will be increased, if the number of variables is 5, then or you can say 6, then 2 raised to power 5, 32, 32 multiplied by 2, 64. You have to write 64 rows. It is not an easy thing. For small things, going on with the truth table is okay, but for the lengthy problems, this truth table is not a good approach. Then what? Use these rules of inference to extract something. Here is an example. Show that the premises, here you have premises started from here and almost ending here. So this is written in sentence form. All the premises are there, conclusion is there, but now you have to prove it mathematically also. Now you have, when you will read it, show that the premises, and the premise is, it is not sunny this afternoon. It is not sunny this afternoon. So this is one sentence ending up here. And it is colder than yesterday. So this is second sentence. And you have and here, not the conditional statement, not the arrow, not the implication. You have and here. So it is not sunny, you can say today. It is not sunny this afternoon, and it is colder than yesterday. So this is premise. Premise is something which you normally write before the conclusion, up above the conclusion. And then, okay, this is first. It is not sunny this afternoon, and it is colder than yesterday. Now we will go swimming only if it is sunny. Here we are already saying it is not sunny. So, okay, it is not sunny this afternoon. I told you already, it is compulsory to read the whole text first. Then you will have an idea that which, for example, if there is some negative sentence, for example, here, if it is not sunny, so this is negative. And when you will read, we will go swimming only if it is sunny. Now it is positive. Now it is sunny is positive. So now it means you have to consider it is sunny P and not negation P. But if you will consider here is P, then that would become negation P. So, and it can create an issue if you have many variables. So it is always better to read the problem first. So we will go swimming only if it is sunny. And if we do not go swimming, Then we will take a canoid trip. This is also a puzzle game. All these questions that you are saying is logical reasoning. And if we take a canoid trip, then we will be home by sunset. I will not give you this sentence and I can ask you, give me the conclusion. I can do like that if I want to tease you strictly, or you can say. So anyhow, so it is not sunny and I have the it is sunny also. So I can say it is sunny is now my P. It is sunny is now my P. You can write this. P is this, Q is this. First you can write it for your guidance. Okay, it is not sunny. Now it is negation P. Okay, clear? Because it is P is the, it is sunny is the P. So it is not sunny is now negation P. And you can represent it with and. And it is colder than yesterday. Okay, this is Q. You can say that this sentence is Q. And what is the reason? You are just writing the premise which is given here. So this is not any rule, okay? You are saying, I am just using the premise which is written here in this paragraph. Okay? I am using only that notation which is mentioned here. Okay. Then what? After writing this one, where you have to reach? You have to reach here. This is the conclusion. We will be home by sunset. So if there is some variable for this sentence, for example, T is the variable for this sentence, then your argument should have to reach there. Anyhow, leave it. Now, what is next? We will go swimming only if it is sunny. We will go swimming only if it is sunny. So here simplification using one. Okay, go here. There is a rule simplification which is mentioned here. Sorry, it is P and Q and therefore P. Or you can see it from here. P and Q implies P. So there are one sentence and another sentence, and then you have some P. So now this is and this one. Consider this negation P as P. So then it would become P and Q. And using that simplification rule, you can write this negation P. Negation. So that would be the answer from here, from this first step. Why we are going to do? Because now we will use this next sentence with that one. We will go swimming only if it is sunny. This we will go swimming, if you are making it R, then it is sunny is the P that you have supposed previously. So R implies P. That is R implies P. So this sentence, you are presenting that sentence with this R implies P, which is premise. So you are again writing premise. Now you are going to use this 2 and 3. And what rule you have applied? Modest tolerance using 2 and 3. What is modest tolerance? Go there. And this is modest tolerance. Negation Q and then P implies Q and negation P. Negation Q, P implies Q. You will have negation P. So Q same almost, but you have negation P. Again, negation Q, P implies Q, therefore negation P. Okay, look at here. What are the same things? These are the same things. So then are and negation will come here, according to that rule. Now, next, go with the next sentence. Now we are here. If we do not go swimming, we will go swimming is something what are. If we do not go swimming, that is negation are. Then we will take a canine trip. So or negation are implies and the next variable for this canine trip. We are using here S. And this is what? This is the sentence that you have used. So that's why you are writing premise. So we are using this premise. And here negation are and this one now you are using something with 4 and 5. What rule? Modest ponens. Now look at the modest ponens.
Yes.
P and P implies Q. So PP is same, you have the Q. So here P implies Q. Consider this negation R as P, okay? So this is same, then you have the S here. Now, what is the next? Now take the next sentence. If we take a canine trip, which was S, I think, previously. If we take a canine trip, which is S, then we will be home by sunset. So that is new sentence. So this S is canine trip and that is T is new variable that you are using. And now do something with this one. Modest ponens again. So this is the same and this T will come here as a conclusion. So these are the things, these are the different premises. This is an argument. I can say this argument is given here. I can also say premises and conclusion is given here. And how you can build this argument written in English into a form of a mathematical. So we used rules of inferences to build this argument mathematically. There is an example 7 in the book. You have to read it by yourself. I think read it yourself. But here rule is different, so we can go on from it. Use resolution. We have time until 2:20. Until 2:20, huh? Or 2:15 you can. So resolution. Use resolution to show that the hypothesis Jasmine is skiing or it is not snowing. So this is one sentence. This is hypothesis. And it is not snowing or Bart is playing hockey. So this is another thing. This employ that, where you have the employ, it means that now the arrow. Employ that Jasmine is skiing or Bart is playing hockey. Use resolution. Resolution is a rule here. The last one. And what is the form? P or Q. Negation P or. And then you have, these are the same thing to Q or. Mostly students' faces are just like that. Previously. Anyhow, innocent, what happens? It is due to Som or something else. It is due to fasting or something else. Your face is, you're very much serious. So anyhow, use resolution now. So you have to convert it into that form. So let P is what? It is snowing, sorry. Here it is snowing is positive, here it is snowing is negative. So it is always better to keep positive with P and then you can put the negation. So that's why it is snowing, which is P. And Q is what? Jasmine is king. This one, Jasmine is king, is now Q. And R is what? Bart is playing hockey. It is snowing, already done. Bart is playing. Bart is playing hockey is the R. Now we can represent the hypothesis. This is hypothesis, the first one. This whole sentence up to here. Now we can represent the hypothesis. It is not snowing, negation P, or due to this or, we have the disjunction. And Q, Jasmine is king. And Q, which is this one. We have said it is Q. So negation P or Q. Okay, up to here it is okay. And then it is snowing, which is P, or Bart is, which is R. So P or R. Due to this or, we have represented this R respectively. So these are the hypotheses. If show that these are the hypotheses, this one and this one employ that. Therefore, now you can write things like that. Using resolution. Now we will use resolution on these two things, on these two premises. And then we have the preposition. If you will use, so this negation P and P, okay, same variable. So this Q and R. This is just for keeping it in our mind. This is just a trick to keep that whole rule in mind. Q and R. Otherwise, you can just go into that table and you can say PR and negation, and then you have Q and R. Resolution. So that resolution is now here. And how you can say it? Q is what? Jasmine is king. And R is what? Bart is playing. Jasmine is king or Bart is playing. Jasmine is king or Bart is playing. So you can just apply resolution and you have your answer. And that answer is the same as it is written here. And you can do that by using resolution rule. How much is left? 12 slides are left. Rules. Proofs by rule of inference. If you have to prove something, you can prove using resolution rule that you have seen previously in previous slide. And if you have now I am not saying details, I'm going shortly. And if I'm going shortly, then maybe you will feel some difficulty. Anyhow, here in this approach, you will see that we will have something. You can convert those compound propositions, which would be in mathematical form, into the classes. And what is a class or classes? A class is a disjunction of variables. A class would be variables and disjunction between them or between them. Or a negation of variables, or a clause will contain some variable that will contain the negation symbol. For example, here, now, if we have statement like this, P or Q and R, then we can write this statement into this form. Now this is two variables and R, two variables and R. So this is now a class. These are two classes and there is an and between them. So if you have something like that, and if you have to prove something, to modify something, you can use some other rules and convert them into the classes. So anyhow, so this is now converted into, this is a rule existed in some table, but that rule is quoted here for your understanding also. This is one class, but it is a combination with the third variable. I want to break that combination into two variables. So here, the author has broken that combination of three variables into two variables using classes. And if you have statement like that, negation P or Q, then you can represent it with negation P and negation Q separately by using this rule. Similarly, if you have something into the implication form, you can convert it into this equivalent disjunction. So these are equivalent rules, nothing else. These are the rules which you have seen in previous slides. If you are not sure, then go and check in the previous tables that you have seen from section 1.1 to this section 1.7, I think, or 1.6. So now we will use these rules in the next examples. Here, show the premises. So show that the premises, this one and this one, these are the two premises. Show that this will reach at the conclusion this. Now you have to use some rule, modify again. So these are the most difficult questions in this discussion. So anyhow, so this is P and Q disjunction R. This is the same thing I have written here. We can rewrite this premises as two classes, this one and this one, using distributive law, table 6 in chapter 1, section 1.3 maybe. Okay, so you have to go into that table. By using that law, you can convert this P and Q disjunction R into these classes. And now you know what is class, two variables and the OR. And these are only three approaches that you have to use to reach on some conclusion. First is to convert it, always try to convert in classes, then convert negations into this form, and then implications into this form. So you have to keep these three tactics in your mind. And then here, we can replace this R by S. This is also a premise. So we can replace this R by S, and here we have the arrow. So you have to replace this arrow by this thing, negation P in this form, negation P RQ. So it would be negation R or S by that rule. First law, table 7. In this chapter 1, table 7 is only the one label. I have just given the reference. I'm not going there. I have just given the reference. Now after that, you can search for the patterns. Which pattern? You have these two classes here, and now one class here. Can you use some rule to reach at this conclusion? Now you have to think. You have now divided your premises into classes, and now think some pattern here, think some rules of inference here, which will give you the path to reach at this P or S. So here P or R, this first class, and this negation and negation or S, you can use the resolution. You can use the resolution. This R and negation R is same, and P and S is now remaining. That is your answer. Okay, moving fast. Universal instantiation. Time is up. This is easy. Let's see. What it's saying? Universal instantiation. The rule of inference used to conclude that PC is true. PC is some statement for some specific variable. In the domain, you have 20 numbers. If I say 5, 5 is specific in that 20 numbers. If I say 19, 19 is specific. So universal instantiation, which is this one, is the rule of inference used to conclude that PC is true, this PC is true, where C, anyhow, leave it. I don't have the time. 16. You can read it these by yourself. It is ended now from my side. This is the homework which I already given. This is not the deadline. Deadline is today. I will start from the next chapter. You have to read it by yourself. It is theoretically. It is not something. The problems are not given here. Look at here. There is no any problem. Just definition. Just definition. You have to keep that definition in your mind. I will ask. This is good example. You have to read. You have to understand it by yourself. I hope you will understand. And I will start next, inshallah, from next chapter. These are only 4 or 5 slides that you have to do by yourself. Or let's see, maybe in the next lecture, I will continue from here.